Welcome to an elementary synthetic geometry-based introduction to inversion of the real plane with respect to a circle course, episode 25, practice number 7, a practice session which I titled From Japan with Love, or Inversive Geometry Meets Sangaku, because in this episode we will solve our next problem, 26, which is a typical representative of the so-called Japanese temple geometry, or Sangaku. Before we deep dive into the underlying mathematics of this problem, what is or what was Sangaku? Sangaku actually was two things. It was something that was physical and explicit, and it was something that was implicit and not tangible. Physically or explicitly, a Sangaku was implemented as a wooden tablet or a wooden plate on which in color there was printed a description of a mathematical problem that usually came from something that these days in the West we would refer to as the Euclidean plane or Euclidean solid geometry, but there were also Sangaku problems that deal with what we now in the West refer to as the theory of numbers, when we will be given a certain amount of liquid, let's say water, wine, tea, oil. We would also be asked to measure an awkward amount of liquid using an awkwardly sized vessel, a cup or a teapot or what have you. And these wooden plates would be normally hung in a prominent place by the entrance into a Japanese religious building or Shinto shrine. And one of the characteristic features of the physical implementation of Sangaku was the combination of the mathematical content and the artistic elegance or the artistic exquisiteness of their rendering. And here are more typical samples of Sangaku than you can handle, and the purpose of this slideshow is to dunk you or to submerge you into the spirit of the time and give you a little bit of a sense of what was it like to do mathematics in Japan back then and there. Collectively taken as one large whole, the Sangaku phenomenon had an intangible and an implicit aspect to it, which is to say that implicitly, Sangaku were the means of horizontal information exchange across the experts in the field during the so-called Edo or Great Peace period that lasted for 265 years, from the year of 1603 to the year of 1868. And the emphasis and the key takeaway from this aspect of Sangaku is the fact that this information exchange was horizontal. Horizontal as opposed to, let's say this way, horizontal as opposed to vertical, and as far as I'm aware of, as much as the vertical information exchange is slow and inefficient, the horizontal information exchange is much more faster and much more efficient. And here, by information in general in this respect, that information doesn't have to be mathematical in nature or information about physics, computer science, or anything else. It could be, for example, the exchange of the DNA information. And for those who are interested in the subject, here is a book you can read in order to get started. It was written by two people, Fukugawa Hidetoshi and Tony Rothman. I do not know much about the first author of this book, and as far as I'm aware, Tony Rothman is a high school math teacher. The title of this book is Sacred Mathematics, Japanese Temple Geometry. The publisher of this book is Princeton University Press. Here is the ISBN. This is an American way to identify books with a unique number. And this book has 377 pages. It has plenty of illustrations, but the deal with illustrations in mathematics is the same deal as we have in real life with ice cream and jello. There is always room for more ice cream. There is always more room for a jello. And when it comes to illustrations, there is always more room for more illustrations in math. You cannot get enough of those, but the reason I recommend this book is because I personally have read it. This book is very accessible. It is an excellent introduction to the subject matter. You do not need to know anything beyond middle school geometry. And if you read this book all the way through, all 377 pages, you will find various problems that you can solve on your own. And at the end of this book, there is a list of references which will guide you towards other books that you can read in order to deepen your understanding of the subject matter. And even though all the material that we cover in this course and all the material covered in the book that I just described in the previous segment is in general quite elementary, the situation with mathematics that is elementary is quite treacherous because sometimes some students make a false assumption that elementary is easy. In fact, nothing can be further from the truth. Elementary is not easy, and there exist plenty of elementary problems in mathematics that you cannot solve. And the definition of you cannot solve is that you cannot solve this problem no matter how much amount of time, unbounded amount of time you are given. In other words, you will not be able to solve this problem in 1 second, 1 minute, 1 hour, 1 day, 1 week, 1 month, 1 year, in 10 years, 100 years, million years. No matter how much time is thrown at you, you will not be able to solve this problem. That is a definition of the difficulty rating and the definition of you cannot solve this problem. And when it comes to Sangaku, even though, again, all the material that relates to it is quite elementary, as far as I'm aware, this problem remains unsolved, is an open problem in mathematics, at least as of the recording date of this episode, which is early April 2026. And the way this Sangaku problem is formulated is as follows. On a circular segment that is constructed on a chord of length L, this chord right here shown at the bottom has length L. This segment is constructed on this chord of known length, and this segment is cut in half with the perpendicular bisector of L of length M. The red line segment that's shown over here that cuts L in half is designated as M. This perpendicular bisector partitions the circular segment into two symmetrical curvilinear triangles. This one and this one. The two sides are perpendicular, but the hypotenuse, if you will, is curved, is a circular arc. By having this information, you know that by constructing a trivial Pythagorean theorem, we can express the radius of this circle in terms of the material L and M. This is trivial business. We don't need to worry about it. So the radius of the generating circle is known, for example. Now, into the curvilinear triangles, they're inscribed on the one side a square with the side length of S, and into the other such curvilinear triangle, they're inscribed a circle of radius R. So the circle is shown in yellow, the square is shown in blue, perpendicular bisector M in red, and the circular segment shown in yellow with a bounding chord of length L. Now here we define two numbers. The number A is the sum of all these magnitudes, and the number B is the ratio, M to L plus R to M plus S to R. So in some sense, when you gather everything into one fraction, you will have basically a ratio of something in the numerator, something in the denominator, LMR. And the objective of this problem is to express all the magnitudes or all the quantities L, M, S, and R as a function of these two numbers, A and B. In other words, we're on the hook in this problem to construct four functions, 1, 2, 3, 4, by the number of magnitudes or quantities L, M, S, and R, which somehow express each magnitude or each quantity as a function of the numbers A and B. One more time, this problem, as far as I'm aware, is open. It have not been solved, and if I'm not mistaken, it might have been mentioned actually in the book that I just described in the previous segment. Leaving a Sangaku problem that no one knows how to solve aside, we will come back to our Sangaku, whose faithful representation you just saw a second ago at the beginning of this segment. This is an actual copy of what apparently appeared in the book by Fujita Kagen. The book was titled Shinpeki Sanpo. It was published in 1789, and in that book there was this problem that belonged to the Japanese gentleman who went by the name Hotta Jinsuke, and he apparently came up with this problem in 1788, and the statement of this problem is as follows. We're given three generating circles. The bounding generating circle, shown in white on the right side of your screen, the large circle, so to speak, named lowercase s, and inside that bounding generating circle, we're given two circles of radius that is equal to half the radius of the bounding generating circle. These two circles I will refer to as sigma 1 and sigma 2. Let's say this is the circle sigma 1, this is the circle sigma 2. Both of these circles touch each other externally at the point over here. We will designate it in a few seconds. That plays the role of the center of the bounding generating circle or outer generating circle, and the circles sigma 1 and sigma 2 touch the bounding outer generating circle S internally at 2 points here and here. And like I said, if we take r, lowercase r, to be the radius of the outer generating circle S, then the radii of the inner generating circle sigma 1 and sigma 2 will be r over 2. Now, into the curvilinear area that is trapped inside of the outer generating circle and outside the inner generating circles, in other words, in this area right here, they're inscribed two families of circles. I will refer to them as the blue family and the red family of circles, or the blue P family of circles and the red Q family of circles. The blue P family of circles is inscribed as follows. The first blue circle, P1, touches the outer generating circle S internally at this point right here, and it touches the two smaller or inner generating circles, sigma 1 and sigma 2, externally, let's say here and here, and all the consequent circles of the blue family of P circles is inscribed in such a way that the next blue circle touches the previous blue circle and then touches the outer generating circle S internally, while touching one of the smaller generating circles externally right here. This circle shown over here, I marked it as P2, and you see what is going on. Evidently, because the radii of the smaller generating circles are the same by length, the circle P1 is located symmetrically, and then this blue family or even the red family of circles evidently can run also symmetrically into one side and then into the other. But if we solve the problem with one half, we solve the problem with the other half, evidently due to the perfect symmetry of this layout and the configuration of the input objects. Thus, we concentrate only on one half, so to speak, of the curvilinear area trapped between the generating circles. And then we have the next blue circle touches the immediately previous one, the two generating circles, the larger outer one and the smaller inner one, and on and on and on. This family of circles drills down and converges, squeezes itself in between the smaller generating circle and larger generating circle. That is one family, and here the numbering traditionally starts with 1 P1, P2, P3. So I will overload the names of these circles. For example, I will refer to the circles as their names, P1, P2, P3, and so on. But for computational purposes, when it comes to the algebra of this problem, I will refer to the length of the radius of each blue circle precisely as that. P1 is the radius of the circle P1. P2 will be the length of the radius of the circle P2. P3 is the length of the radius of the circle 3, and so on. So Pn will be the length of the radius of the inscribed blue circle Pn. Likewise, the second family of circles, the red circles, is inscribed as follows. The first circle, again, I will overload the name. The symbols Q1. Q1 will be the name and the length of the radius of the corresponding circle. So the first circle, Q1, the red circle, is inscribed in such a way that for the red family of circles, in a sense, you already see what is going on. The blue circles play the role of the outer generating circle for the blue family of circles. In other words, the first circle Q1 from the red family of circles also touches the smaller generating circles externally, and it touches, instead of the outer generating circle, it touches the immediately adjacent blue circle of the blue family of inscribed circles. Then the second red circle also touches the smaller generating circle, let's say sigma 2 in this case, but then it touches the two immediately adjacent circles from the blue family, the circle P1 and P2. The red circle Q3, let's say, will touch the smaller circle sigma 2, and it will touch the immediate neighbors blue circles P2 and P3, and so on. Again, you understand that the red family of circles also zooms in and converges logically under, squeezes itself all the way in between the smaller generating circle and the outer larger generating circle. As again, which circle you pick for the demonstration, sigma 1 or sigma 2, it doesn't really matter. The situation is completely symmetrical. The radii of these, the lengths of the radii of these two smaller generating circles are identical by length. They equal one another. It doesn't really matter. So due to the symmetry, I portray it this way. And of course, this is my, in some sense, not so precise by hand and by eye drawing, but if we put together this drawing mathematically precisely and correctly using any software you like, for example, I use the free software called GeoGebra, then the Hotta-Ginsky problem will look as follows. And for the objective of this problem, apparently the author of this problem, Mr. Hotta-Ginsky, insisted on us numbering the circles of the two inscribed families starting with strictly positive whole numbers 1, 2, 3, 4, 5, 6, 7, instead of starting with 0, 1, 2, 3, as the circles were named, for example, if you remember, in the problem of Chain of Pappus. And the original objective of this problem, as its author formulated, was to express this number n, as in 1, 2, 3, 4, 5, 6, 7, as a function of the ratio of the radius r to the radius Pn, and as another function that is a function of the ratio of the length of the radius r to the length of the radius of the nth circle inscribed from the red family Qn. But for us, we will first solve this problem, or our objective will be to construct these two functions. The length of the radius of the nth inscribed blue circle, Pn, is a function of the ordinal number of that circle, and the length of the radius of the outer generating circle, Pn, as f of n and r, and the length of the radius of the nth red inscribed circle as a function of its ordinal number n and the length of the radius r. While this problem can of course be solved without the machinery of inversive geometry by relying on a theorem that ties together the length of the radii of three circles positioned, for example, as shown over here, P1, sigma 1, sigma 2, and the first inscribed red circle, Q1, we of course will solve this problem using the machinery of inversive geometry precisely. We will see that that solution is very straightforward, elegant, and crisp in some sense. And the fun part of doing mathematics is in general is to kick around different ideas, as it is usually the case in mathematics and in theoretical physics and in computer science. The first ideas are probably and most likely are the wrong ones. They do not lead us to victory. And here one of the reasons why I included this problem in this course is, of course, this problem can be solved in a fairly expedient fashion using the machinery of inversive geometry. And the second reason why I included this problem in this course is because I would like to showcase another phenomenon in mathematics, which is basically the following. The more problems in a given area we solve, the more likely that we will be able to solve the next related problem. And here, the moment you cast your eyes on this problem statement, on the configuration of the input objects, you should instantly recognize that this is just a slightly shaken but not stirred reincarnation of the problem that we solved in the past. This is the Chain of Pappus problem. Its coordinates are given over here. In this course, we solved this problem in episode 17, seminar 8, in my free book, Inversive Geometry for All. That will be chapter 12. Either way, that's problem number 18. And a tactically advantageous solution of the Chain of Pappus problem, as a friendly reminder, looked as follows. And as you recall the Chain of Pappus problem, then you will see that in this specific Sangaku problem, what is the role of the circle sigma 1? Well, in the Chain of Pappus problem, we had the circle numbered K0. Remember, it was sitting on top because the circle sigma 2 was larger in radius. It ended somewhere over here, for example, but it could be smaller, of course. But the point is that in the Chain of Pappus problem, we were given two generating circles, the outer generating circle, bounding circle S, and the circle sigma 2 that touched each other at the point T internally. And the inscribed family of circles was basically this almost blue family of circles, plus the circle that in this problem plays the role of the circle sigma 1, which is a given generating circle. But in the Chain of Pappus problem, that was the circle K0. Remember, this was K0. So in some sense, we already see a very close resemblance of this problem to the Chain of Pappus problem. And what is the sane thing to do, or what is a sound strategy? Well, we had one way of doing things in a similar problem, and that way of doing things led us to victory. We chose the successful parameters of inversion. So the natural thing to do is to try that same inversion in this problem that is related, and lo and behold, that inversion actually works here. It is a successful inversion. It will take us to victory, and the parameters of this inversion are the circle of inversion C. I do not show it over here for the reasons that I will explain in a second. The center of inversion will be the point T, where the outer or bounding generating circle S touches the inner generating circle sigma 2. The tangency point over here is internal, but this is the point T shown in red on the bottom right of your screen. So the radius of inversion over here, rho, can be any real number that is strictly positive. The power of inversion is positive, plus rho square. And as I mentioned many times in the previous lectures in this course, in some situations, the specific magnitude or the length of the radius of inversion is irrelevant. It plays no significant or essential role. And in this episode, we will see precisely why. Instead of setting the radius of inversion rho to the positive unity right away and just not bothering with it at all, we will pretend that in this specific case, the radius of inversion rho, on top of being strictly positive, it is not the positive unity, it is some arbitrary number, 17.5, square root of 5, whatever. And we will see where that assumption will lead us. In other words, one more time, the center of inversion is the point T, the point where the outer generating circle S touches the inner generating circle sigma 2. The power of inversion is positive. The radius of inversion is irrelevant. Any strictly positive real number will do. The number of inversions is 1. Our composition of inversions in some sense collapses into just one inversion, and under that inversion, which is basically fundamentally is the same parameters of inversion that we chose for the chain of Pappus problem, what will happen? Let us think about this together in an expedient fashion. We have two circles, the circle S and the circle sigma 2, passing precisely through the center of inversion based on the corresponding family of theorems. We know what? We know that these two parallel circles will be taken into what? They will be taken into two straight lines, neither of which passes through the center of inversion. And these straight lines will be what? Well, their angular relationship between them will be the same as the angular relationship between the pre-images of these images. In other words, if the circles S and sigma 2 are parallel at point T, then their images will also be parallel. In other words, the circle S will be taken into the straight line S prime. The circle sigma 2 will be taken into a straight line sigma prime 2, such that the straight line S prime is parallel to the straight line sigma prime 2. I showed the images of the pre-images in this case in yellow. So this is the image of the outer generating circle S, the straight line S prime. This is the image sigma prime 2 of straight line. This is the image of the circle sigma 2. And lastly, what do we need to invert as the first step? Well, we also need to invert the circle sigma 1. And the circle sigma 1, what is the characteristic property of the circle in the chosen inversion? It does not pass through the center of inversion T. The circle sigma 1 passes through the center of the outer bounding circle S, but it does not pass through the center of inversion point T. Consequently, that circle will be taken into a genuine circle that also does not pass through the center of inversion T. In other words, our circles S and sigma 2 that do pass through the center of inversion are taken into parallel lines that do not pass through the center of inversion. But we also remember that under inversion of the real plane with respect to a circle with any power, positive or negative, the tangency points are preserved. That means that if the circle sigma 1 touches the pre-image circle S and the pre-image circle sigma 2, it means that the image of the circle sigma 1 or the circle genuine circle sigma prime 1 will necessarily touch both of the images of the circles S and sigma 2, which are what? Not only straight lines. These images are not only straight lines, but these are the straight lines that are parallel. And in some sense, that means that the distance, the orthogonal distance between these two straight lines at any point is one and the same. Measured here at this point, the distance is blah. Measured from this point, it's also blah, 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 the same distance. That means that our circle sigma 1 will be reflected under the chosen inversion into a genuine circle shown in yellow, sigma prime 1, such that this circle will be squeezed between the vice, so to speak, formed by the straight line S prime and sigma prime 2. And you already see what is going on. I already started preparing for you what will be the images of the blue circles, but you will figure it out on your own without my help. And before we move on further and dig the rabbit hole for that particular inversion of this problem, I recommend that you experiment with other inversions. Once you see what is going on, evidently all our blue family of circles will be what? It will be also squeezed in the vice formed by the straight lines sigma prime 2 and sigma prime. But that, what does it mean? It means that all these circles, the reflected blue circles, will have one and the same radius, pretty much in exactly the same way in which we obtained a similar situation in the chain of Pappus problem. Remember, it was a childish solution. All the inverted circles had the same radius, and the distance from the center of each such circle to the line of centers was also a baby 2n times r, the radius. This is it. So we know this is the place where we gain the tactical or competitive advantage with the transform and conquer problem solving approach. Transform, solve a much easier problem. Reverse transform the solution of the easy problem into the solution of the original, more difficult to solve problem. But I recommend that, as any student of mathematics really should do, play with other ideas. For example, again, what other advantageous point? I'm not talking about this point because, again, this point is similar to this one. If we flip everything in uh, uh, with respect to this point, invert the parent plane with respect to this point, that's not fundamental difference. The difference comes, for example, from here. Look at this. At this point, that place that is the center of the bounding, outer bounding circle S. In this circle, how many, at this point, how many circles meet? Also, two circles meet. And that means that the circles sigma 1 and sigma 2, these circles are parallel because the tangents constructed to both circles through the point of contact will be parallel. The angle between them is what? Well, it comes from the countably infinite set of real numbers k times pi, where k varies as 0, plus minus 1, plus minus 2, pi, and so on. But 0 is a very pleasant representative. So the angles between these tangents is 0. Consequently, these circles are parallel. They will be taken into what? Also parallel straight lines. So that is another parameter, set of parameters of inversion that also looks promising, because then these two circles will be flipped into two parallel straight lines. Between them, certain things must be squeezed, but in this case, what can be the circle of inversion? Maybe experiment with this. If this is the center of inversion 1, why not take S to be the circle of inversion with positive power? Because then the circle of inversion will be taken into itself. We will flip the circles sigma 1 and sigma 2 into two parallel straight lines. All the entire family of blue circles also must be poured in between these two parallel straight lines, and so on. So maybe that also will lead you to victory. Experiment, see what you come up with. Maybe share your success story with us or share your failure story with us. This is just as informative. Meanwhile, we will proceed with this set of parameters of inversion. The center of inversion will be t, the power inversion positive, the radius of inversion doesn't really matter. And done again, this is my by hand, by eye drawing, but done professionally, this set of reflected objects will look as follows. And there's a short quiz of your understanding of what is going on in this particular problem. Explain to yourself or to your fellow classmates why, under the chosen inversion, the blue P family of circles will be reflected into a blue P prime family of circles, where each such reflected blue circle, P prime n, P prime 3, 2, P prime 1, and so on, will have one and the same radius. Exactly. Once you generated this explanation, you will see that we can designate the length of the radius of each reflected circle, P prime n, P prime k, P prime 3, P prime 2, P prime 1, and so on, with just one number, P prime. Likewise, y under the chosen inversion, the set of the original red Q circles will be reflected into a family of red Q circles primed, which touch the straight line sigma prime 2 and the blue reflected circles P prime K. Exactly. The answer to all of these questions is because inversion of the real plane with respect to a circle with any power, positive or negative, does preserve the points of tangency, which means that if the original blue P family of circles touches the circles sigma 1, sigma 2, and then the circle S, the reflected blue circles will also touch the images of the circles, and that will be the first circle sigma 1 and then a pair of parallel straight lines. Likewise for the family of red Q circles, if the original red Q circles touch the circles P from the P family and the circles sigma 2 and S, then consequently the reflected circles will touch the images of what? They will touch the images of the blue circles, which are these circles of equal radii, P1, P2, P3, and so on, and the image of the circle sigma 2, which is the straight line sigma prime 2. And the moment you understand that fact, you will also realize that not only the chosen set of parameters of inversion eliminates the variance across the length of the radii of the blue reflected circles, it also eliminates the variance across the lengths of radii of the reflected red circles. In other words, all reflected blue circles have one and the same radii P prime. We will designate it with that symbol. And all the reflected red circles also have one and the same radius. The length of the radius of all these circles is the same, so we will designate it as follows. Q prime n is the same as so on, Q prime k, Q prime 3, Q prime 2, Q prime 1, and in general this will be just one symbol, Q prime, for the length of the radius of each reflected red circle. The situation over here is only marginally more complicated or marginally more complex, but nothing that we cannot handle. And again, the moment you realize all this situation with the reflected circles, with the chosen parameters of inversion, you do not really need me. You should be able to carry the solution of this problem correctly, completely on your own. You can come back and compare your results with our results for a reference with the correct response, but you already know the overall computational template. The template is as follows. We will use this distance from the line of centers to the center of, let's say, kth reflected blue circle. We know that there are two Pythagorean theorems over here, one through the tangency, one through the center, and then the other Pythagorean theorem on this triangle. The point T will play some magnitude, will play the role of the power of the point T with respect to a certain circle. So two applications of the Pythagorean theorem, the power of a point with respect to a circle, and the workhorse relation that captures the algebra of inversion of the real plane with respect to a circle, and pretty much following in the footsteps of the computation that we carried out when we were solving the chain of Pappus problem, we can solve this problem. And first we will start with the family of the blue circles Pn. As such, let us first square away our relationship with the blue circles, with the blue family of circles P. To that end, we observe carefully that let, for example, A0 be the point where the outer generating circle S and the circle sigma 1 touch, and let, where is it, the center of the circle S will be the point B0. And under the chosen inversion, we can already see that the point A0 will be thrown into this point right here, A prime 0, and the point B0 will be flipped into the point B prime 0 over here. And the points B prime 0 and A prime 0, these are the points. They will actually determine or define the vise into which all our reflected circles are squeezed. So now we basically write down the childish observation that the radius, remember this one, the length of the radius P prime of each and every reflected blue circle, P prime K, will be equal to the length of the radius of the reflected circle sigma prime 1. These circles all sit between the same pair of parallel lines. And what is the radius of the circle? Well, twice this radius plus this distance from T to AO gives us the distance from T to B prime 0. So in other words, twice P prime plus the distance from the point T to A prime 0 gives us the distance from the point T to B prime 0. From here, we instantly find that P prime, the length of the radius of each reflected blue circle, is half the difference between these distances, but we already know the recipe. This point is the image of the point B, this point is the image of the point A, B0, A0, and we write down the algebraic representation of inversion in this case. Remember, condition 3, definition 1, the product of these distances is the distance of interest over here times r, because the distance from T to B0, let's see, from T to B0, remember B0 is the center of the circle S, so this distance is r, radius, is equal to rho square, some mysterious non-zero radius of inversion, and the same deal applies to the points A prime 0 and AO, except that the distance AO, look at this, from T to A0, A0 is what? Twice the radius of the outer circle S, twice R. So we know this distance, we know this distance, rho square over R, rho square over 2R. We need to take half, so for the length of the radius P prime of any reflected blue circle, we have rho square over 2r minus rho square over 4r comes out to rho square over 4r. We have this result over here. So in some sense, we already solved the problem for the length of the radius of the inverted circle. There it is. This material is our choice. You will see in a few seconds that it's really irrelevant. It will disappear. And this is what we are given. This is what we need to find. R is the one of the arguments of this function. So now we do pretty much the same thing with that we did in the Chain of Pappus problem. Again, I'm providing this just as a guidance for you. You should be able to swing it on your own. We connect the point uppercase P prime n, that is the center of the nth reflected circle, lowercase p prime n. We connect it with the point T. On that point lives the center of the pre-image circle. This is the difficult problem over here when our blue circles are inscribed in between two circles. And we also construct the tangency point, so we set things up for the power of a point with respect to a circle thingy. Once this point over here will be a tangent through the point T to the nth reflected circle T prime n, and it will have its body point over here Tn, and the game is over. We connect the center of the circle with the tangency point. We connect the center of the corresponding circle with the tangency point, and we have two triangles, T, Tn, Pn. This right triangle over here, T, Tn, Pn, with the magnitude of the interior angle at T prime n is 90 degrees pi over 2 radians, and the triangle T, Tn, Pn is right here, T, Tn, Pn, this guy, the smaller one, T, Tn, Pn, T, T prime n, P prime n. And these triangles are similar, and you should be able to explain why they're similar. And, well, you should be able to explain that we have two angles here, pi, they share the same angle. It means their remaining angle the same. So by angle, 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 they're similar. And from the similarity, Euclid's Elements, book 6, proposition 4, the length of the sides in such similar triangles about equal angles are in same proportion where the corresponding sides lie at opposite equal angles. So here the length of the radius Pn already, this is the guy we want to find. This guy right here relates to the length of the radius right here. This p prime and pn, the same as the distance ttn. This is the side, not the hypotenuse, but the side of the right triangle, relates to the distance t prime n, this distance right here. And here, from here, we write down the expression for pn in terms of p prime. Remember, we know p prime, we don't worry about it, we know what it is. This is this ratio, but we go back to the fact that the points t prime n and tn are the inversive images of each other. The product of these distances is rho square, express ttn. We have it, slug it in here. You have this expression over here. And at this point, look at this, you have the square of the distance t prime n. And what is the square of this distance? Well, that's the power of a point, or power of the point t with respect to the reflected blue circle p prime n. And that power is represented as the difference between the distance, square of the distance t p prime n. That's the distance to the center of the circle. Remember, that's the power of a point with respect to a circle. That is how we define it. The distance from the point to the center of that circle minus the square of the radius of the circle. But the square of the radius of the circle is already known to us. Game pretty much over, except that we need to fight the fight with this quantity, with this distance. But you already know what will happen in the next few seconds, because the distance t p prime n squared, or just the linear distance itself, is what is the hypotenuse of another right triangle that's hiding in plain sight. And in that triangle we will draw in a few seconds. I will take the time to erase all this, keep good records of this, but we will draw this side. And look at this. This is this distance is baby distance. We can count it very easily. P prime, one copy of P prime, another copy of P prime, another copy, bam, bam, bam. And we can take it home and bring the computation of the square of this distance to an expression that has nothing but the material that we are given and known. Remembering that the radius p prime of every reflected blue circle is computed over here, rho square over 4 times r. R is the radius of the outer generating circle. As we proceed with the remaining computation as follows: the square of the distance tpn, the distance from the t to the point pn, which is the center of the nth reflected circle, is the hypotenuse of this right triangle right here, t O prime 0. This is the center of the circle sigma prime 1, all the way to this point right here, the center of the nth reflected blue circle p prime n. This is it. So we write it down as the hypotenuse. This is the sum of squares of the sides. The distance t from the point t to the point O prime 0, from here to here, and from here, from O prime 0 all the way to Pn. This distance right here is the analog of our distance dn from the chain of Pappus problem. If you pull it up, you will see that in the chain of Pappus problem we had 2n times the radius of each reflected circle. That is because we counted this circle as a reflected circle. In our case, this is not the family, so we need to offset it by 1. Our 0th circle, if you will, is the circle number 1, the first one. That is why we offset this numbering by 1, 2 times n minus 1. You see, 1, 2, 1, 2, so it's always twice the distance. In the chain of Pappus, this was also the reflected circle, k0, remember? But in this problem, it is not. We start numbering from 1, starting from this circle right here, so we have this trivial relation. And for the distance from the point t to the point O prime 0, from here to here, this is evident. It's this distance, r plus the radius p prime. And we have it right here, ta prime 0, ta prime 0 plus the distance a from a prime 0 to O prime 0. This is not half, I'm sorry, this is our distance p prime, and this is what we have. We computed this distance, remember, in the previous segment, plus this distance right here. So that was 1/2. 1/2 plus 1/4 becomes 3/4. There we go. Rho squared times 3/4 times r. R, again, is the radius of the generating circle. And this is it. The rest is just arithmetic that flows effortlessly. We come back over here and we proceed. We have this distance over here. This guy comes from here, comes to here. When we square this guy, we get rho to the 4th power, 9/16 r squared, 9/16 r squared, plus the square of this number right here. This is 4n minus 1 squared, p prime squared. This guy, p prime squared, and we know p prime. So it's not really complicated. It's just middle school arithmetic. So we now come back to the original distance from the point t to t prime n. From the point t to t prime n, right here, remember, it's the power of the point t with respect to this here reflected and blue circle. So it's what? It's the square of the distance that we just computed. This guy, t p n prime, this distance right here. Let me show you. It's this way. It's the distance right here from the point t to the point pn right here. See this guy right here? And minus the square of the radius, minus the square of the radius p prime. But again, this is all this material may look a little scary, but it's not. I mean, this is known material. Look over here, and the rest is known material. Game over. So we now carefully open up the parentheses. We do the collection. We don't forget that we have the rho squared in the p prime. So the square of p prime becomes scaled by rho raised to the 4th power. You see here, 4th power, 4th power. Don't forget the 4th power is over here. But this is, again, elementary arithmetic, nothing to write home about. And this is it. We come back, we pull up our expression that we had a few seconds ago at the bottom of the board, bottom center of the board, and we write it down like so. Rho squared times 1/4r times rho squared times 4r squared. And look at this. Rho squared times rho squared becomes rho raised to the 4th power. And what do we have in the denominator here? 2 times rho raised to the 4th power plus 4n plus the n minus 1 squared, this term right here, times rho raised to the 4th power again. So here, look at this. Rho to the 4th. Rho to the 4th power, and here square and square, they cancel each other out. See, this is the magic, if you will, of inversive geometry. The magnitude of the length, or the actual quantity, the actual value for the length of the radius of the circle of inversion is irrelevant. We could put any non-zero real number to correlate it meaningfully with the geometric interpretation as the distance. It cannot be negative, 0 or more, 0 not interesting, or more. There you go. So we might as well put this value to, set this value to the positive unity 1 and forget all about it. And there we go. So we have our expression for the length of the radius of the nth inscribed blue circle as the function of n and r is requested over here, that looks as follows. R, the length of the radius of the outer circle, is divided by 2 plus n minus 1 squared for all n greater than 1. But when n is greater, when n is actually equal to 1, then this is, again, elementary chase of the Pythagorean theorems, and we will take care of it in the next segment. Which is to say that in a lightning round, we take this point B, where is it? Or we take the point, this one from here, the center of the circle, sigma 1, we connect it with the center of the first blue circle, P1. We draw the straight line through the center of the bounding circle S. We get the right triangle. And to that triangle, we apply the Pythagorean theorem, which says what? Look at this. This radius is P1. This radius right here is r over 2. And what is this distance right here? Well, for this circle, the entire distance is r minus this guy, twice r. So this distance will be r minus 2p1 plus another p1, r minus p1. So there you go. This is our Pythagorean theorem for that triangle. r over 2 plus p1 squared, that's the hypotenuse. This hypotenuse right here from here all the way to here. Then r over 2 squared, is this distance right here. This is the radius of the smaller circle, sigma 1, this guy, plus this distance right here. And this distance is what? R minus p1. That's it. The rest is just sub-middle school arithmetic. Open up the squares, and then notice what? P1 squared and P1 squared cancel each other out. R squared over 4, R squared over 4 cancel each other out. Negative 2RP1, positive RP21. Bring sum 3RP1 equals to R squared. Remember that R is not 0. Kill 3P1R. So from here, P1 is R over 3 for n equals 1. So combined with this relation right here, we solve the problem for the blue family of P circles completely. Onto the red Q family of inscribed circles here, since we already know the radius of the first inscribed blue square P1. In hot pursuit, we take care of the very first inscribed red circle Q1. Here, the deal is exactly the same. Remember that the centers of the generating circle as outer bounding circle, this point right here, the center of the first blue circle P1 and the center of the first Q circle Q1 are all what? They're all collinear. They all sit on one and the same straight line right here. So the arithmetic of computing the radius of the first red circle Q1 is exactly the same as the arithmetic for computing the radius of the first blue circle P1, except that here we take the difference, the symbol Q1, R over 2, this distance right here is exactly the same. The only trick is to figure out this distance, and it's quite straightforward. Remember, we have twice the length of the radius P1, plus, because the red circle and the blue circles touch, we have one copy of Q1, and this is what we have right here, R minus 2P1, but P1 is known to us, it's R over 3, so this distance, R minus 2/3, 1 minus 2/3 comes out to 1/3. Once we open up the parentheses on both sides, look again, square over 4 cancel out, 2/3 flies to the left, 2/3 plus 1, 5/3, Q1R equals R square over 9, R square over 9, that's the first square, the square of the first term, and since R is not 0, cancel R, cancel square, there we go. We have 3 on this side, 9 is representable as 3 times 3, cancel, and there we go. The length of the radius of the first inscribed red circle Q1 is R over 15, n equal to 1. And as a final step of our computation, we do to the red circles the same thing that we did to the blue circles. In other words, we play out exactly the same script. Fundamentally and structurally, it will be the same. That is, first, we want to compute the length of the radius of all the uniformly reflected image circles. And then we tie up this radius of the reflected circles with the radius of the original circles. Game over. Here, however, one small caveat I want to bring your attention to is that we will use the theorem number 31. Remember that we proved this nifty little theorem, which establishes an algebraic relationship between the radii of the original and reflected or inverted circles. This formula is over here. This is the algebraic embodiment of the theorem 31, which says that the length of the radius of the inverted circle, R prime, is the length of the radius of the original circle, R, times the ratio of the square of the radius of inversion, and the difference between the square of D. What is D? D is the distance from the center of inversion to the center of the original circle, and the square of the radius of the original circle. Game over. Now, in our case, what is R prime? R prime is Q prime, the length of the radius of all the red reflected circle. The entire family of reflected red circles has one and the same radius, Q prime. Boom, we write it down. Q prime is equal to What plays the role of uppercase R in our case? Well, it's the length of the radius Q1, the length of the radius of the first inscribed circle. This is the original guy that gives birth to them all. In my drawing, of course, it looks horribly out of proportion, but that is the idea. What is next? Next is the square of the radius of inversion, rho squared, a mysterious, strictly positive real number. Wonderful. Q squared 1, this guy we already know. And what is D? Is the distance from the center of inversion, which is what? The point T, and the center of the original circle, Q1. Look over here. I tried to portray it for you in red. Hopefully you can see it. Uppercase Q1, right here, this point. And the distance TQ1 also is what? That distance is the hypotenuse of the right triangle. Remember all the points, B0, Q, and the center of the first blue circle, they're all collinear. We actually worked with this distance not so long ago, a few seconds prior in the previous segment. So we applied the Pythagorean theorem to this here, T, B0, Q, uppercase Q1, right triangle, and this is what we have. D squared is equal to square of the distance between the points T and Q1, which is R squared. Where did R squared come from? Well, R squared is exactly this distance from T to B0, R. And now this little itsy bitsy spider thingy here, which is what? Well, it's R minus 2P1 minus Q1. Remember that P1, we computed in the previous segment right here, R over 3. 1 minus 2/3 is 1/3. And Q1 is what? Is R over 15. So 1/3 minus 1/15 will be what? 5 minus 1, 4. 4/15. So there you go. R squared plus 4 over 15 times R, the whole caboodle squared. Square, square, square. Now we take this guy and we put it into the denominator of this expression. So what do we have? Instead of Q1, we put this number right here. R over 15 times rho squared, divided by D squared. This is guy right here. We simply take this difference and slug it in here verbatim. Minus the square of this guy, R squared over 15. And what remains here is elementary sub-middle school arithmetic. Look at this. 15 in the denominator will crawl through the denominator here, and it will clear out the 15 squared in the denominator of the denominator. So what will we have left? 15 R squared plus 16 over 15 minus R squared over 15. 16 over 15 minus 1/15 comes out to 5. 16 15th minus 1/15 comes out to 15 over 15. That's 1. 1 plus 15, 16. 16 R squared in the denominator, but we have one copy of R over here. Game over. Rho squared times 1 over 16R is the magnitude of the length of the radius of each and every reflected red circle Q prime. And as a final computational leg of our journey, look at this. We take the center of the image red circle, Q prime something, and then we connect it again with the center of inversion. We get our line of centers. Of course, in my by hand drawing, it doesn't look realistic, but when you do things with the software correctly by the book, you will have precisely the line of centers that goes through the center of inversion. You can construct a tangent to the nth, let's say, circle, red circle, and that tangent will also be tangent to the original circle. So you'll have the same situation as you have over here. Basically, we take this setup that we had with blue circles and we portray it or lay it on top of the family of red circles. Exactly the same. Again, conceptually, structurally, fundamentally, is the same thing, nothing new. So here, by playing games with the same right triangles, by angle, these triangles will be similar, and similar triangles, the length about equal angles are in the same proportion, yada yada. You already know the drill. From these triangles, we construct the same exact ratio. You can pull up your records, and instead of Pn and P prime, we slug in Qn and Q prime. The game is over again. But not to be confused, here the point T prime n and Tn, if we encounter it, it's not these guys, it's the red guys now. So in some sense, adjust your thinking. Maybe even I can make it more easier for you to comprehend. Here we will have the red point Tn. You see red point T prime N, red point T prime N, these points T prime N right here, T prime N right here, and there will be corresponding point Tn right here. Likewise, we will have the points Q prime, and when we come to what? The distance, the square of this distance is what? Is the power of a point with respect to a circle. The power of which point? T, with respect to which circle? The nth reflected red circle. And this is the manifestation of this power of a point with respect to a circle. There we go. Now, from the triangle T, Q prime 0, Q prime N, what is Q prime N? Q prime N is this guy right here. And Q prime 0 will be this point right here that sits on the line of centers. I will not be already writing, it's already incomprehensible mess, but when you pull up the free PDF file as a chapter from my book, you will see everything is nice and neat, it falls into place, it's not really complicated. So from this triangle, we have that the distance, the square of this distance will be, again, remember we now use what? This triangle, and this triangle. The triangle that hypotenuse of this triangle is the line of centers of the original circle and the image circle. So this is where this theorem comes from. Again, maybe I can mark it for you. Q prime 0, Q prime N. You understand what's going on. The red family of circles, Q prime 0, Q prime N. Now, this distance, Q prime O, Q prime N, let's find it on our drawing. This is this distance right here, from here to here. Look at this, see, this distance right here. It's not complicated. But let's think about this together. Look at this. The family of red circles sits nicely and neatly tucked between immediately two adjacent tangent reflected blue circles, and it also touches our straight line sigma prime 2. What does it mean? It means that if we take the center of that circle and project it orthogonally, we will hit precisely the point of tangency of these two blue circles. And for this circle too, boom, right here. So what is this? Well, this distance right here is twice p prime. Nothing changes, so this is, we have twice p prime almost. But this time we put, what do I have to put? We have to offset by 1. Remember that we do not have the first. We computed the radius of the first circle already. So we offset things by 1. This is our relation. And after that is just smooth sailing. The difference T, the distance, I'm sorry, from the point T to the point Q prime O, represented right here as this distance T B prime 0, this distance, minus this distance right here, the radius of the circle Q prime, this distance right here. See, right here, this distance right here. From the point T to the point Q prime O, to here, to this right here. See, it's this distance, the entire distance, minus this little bit that we already computed, Q prime right here, this guy, Q prime. So once we do the arithmetic, we know this, Q prime we computed in the previous segment. You will have rho squared times 15 over 16r, and the rest is just middle school arithmetic. You put this expression back for the distance between the points T and Q prime N. T and Q prime N right here, this guy. We obtain this expression rho raised to the 4th times 15 square over 16 square r square, this guy, plus the square of this distance, 2n minus 1 squared times p prime. Don't forget, this is p prime, not q prime, but p prime. P prime here, p prime here. And then for the distance, for the square of the distance between the points T and T prime N, in other words, the distance from here to here, this distance right here, see? Don't forget, we have to, for this distance, where is it? This guy, see, we have to subtract Q prime squared. So this is what we do. We take this expression, this guy here, minus Q prime squared, this guy. And once you do, again, all the arithmetic, I will not bother with the intermediate computations. You can double check my arithmetic. You will obtain this expression, rho to the fourth over 8r squared plus rho to the fourth 2n minus 1 squared over 16r squared. So here, evidently, you will have what? Multiply by 2, bring it to common denominator. Again, this is all trivial computations, but don't forget, this square sits in the denominator of this expression over here for Qn. So this horrible expression goes to the bottom, so to speak, second floor, or the basement. So you expect that this material will be somewhere in the denominator. And obviously, that is the case. Qn comes out to be, let's say, as a function, let's rewrite it maybe more politely. Qn as a function of r will be r over 14 plus 2n minus 1 squared for all n greater than 1. Now, where did 14 come from? 14 came from the following fact. When I was doing these computations, I came across this expression, 15 squared minus 1. What do you do? Well, it's a difference of squares. 15 minus 1 times 15 plus 1. 14 times 16. 16s evaporate, and this is what you have, 14. The number to watch out here is 14. So this is the relationship together with the one that we obtained previously already solves the problem completely for the red family of circles. And the game is over. Once we write down all the results carefully, we can do with these results anything that we wish. We have this expression over here for the length of the radius of each and every blue family of p circles for all n greater than 1. Here's the expression for the very first radius of the first blue p circle. Likewise, here is the expression as a function of the ordinal number and the radius r of the outer generating circle for the length of the radius of each and every red q circle. It's shown over here. Don't forget we have 14, the magic number. Again, for all n greater than 0, here is the result for the very first red q circle, q1, r over 15. For the radius of the first blue circle, it's r over 3. Again, if we construct the ratio of these two relations, of these two quantities, then the radius r, the magnitude of the radius r evidently evaporates, and we have a nice rational number. Depending on how we flip these ratios, up to you, 14 plus 2n minus 1 squared over 2 plus n minus 1 squared. And as the author of this problem originally wanted, I think he was looking for this formula, but we can write down this formula over here, the natural number, or the, let's say, whole positive number n as a function of the ratio of the length of the radius r of the outer bounding generating circle to the length of the radius of the nth inscribed blue p circle. It's given over here, 1 plus square root of r over pn minus 2. There is no mystery over here. The inverse function is quite straightforward. We take this denominator, put it over here. We take p, we put it at the bottom. We carry 2 to the other side. Minus 2, we take the square, we add 1. Game over, nothing complicated. Likewise, over here, we take r, we keep it here. We move q from the left to the right. We take the denominator, move it to the right. So we subtract 14 from the ratio. R over Qn minus 14, we do what? We take the square root, because the square over here, add 1, and we divide everything by 2 because we have 2 in front of n. Game over. So n as the function of the ratio r, length of the radius of the generating outer circle, to the length of the radius of nth red q family of circles, is 1/2 times 1 plus square root of r over qn minus 14, close paren, game over, problem solved. And admittedly, here or there we had a little bit of somewhat boring, somewhat tedious computations, but fundamentally we did not have any issues with solving this problem precisely because the inversive geometry gave us the tool to gain a competitive advantage. And what was this competitive advantage? Well, it was the uniformity of the circles, of the reflected circles from the blue family, and the uniformity of all the circles that were reflected for the red family of circles. And fundamentally, this is it. Like I said before, see if you can make it work when you take the center of the outer circle S as the center of inversion, flip these two circles again into parallel straight lines, maybe make S as the circle of inversion. See where that takes you, but this is it for the problem number 26.